Okay, thank you very much, Jean-Philippe. And I should begin by saying thanks a lot to all of the organizers of this very nice event. I'm super happy to be invited to this place. It's my first visit to CIRM, and I was excited. There's the mountains, and I'm a rock climber, so I brought some climbing gear. So if anyone is interested, we can go on Wednesday on a climbing excursion. I also happy to have Jean-Philippe here as a chairman, because this is work, it essentially goes back to work we started like 15 years ago. So I'm happy to give a little update on what's going on. So these are obviously some vortex configurations here to give you an inspiration, and it's a joint work with these people. So there's some PhD students, master students, postdocs, and who have been in Uppsala or in elsewhere. Theo is in Italy, in L'Aquila. Okay, so I'm gonna cut straight to the chase and sort of give you the physics background and motivation, and then we will go to the definitions later. So essentially, I'm working with anyons, so we have seen a lot of bosons and fermions. Well, we will see more of those. But in these cases, it's a perturbation, and you have some expansion, you have some conjectures to work with. The problem here is that we don't have so much conjectures. So we really first have to figure out the conjecture, and then we can try to prove it. So I will sort of give you some overview of what has been known and what we can do at the moment. So anyons just means that we're in 2 dimensions. Maybe I just draw a quick picture to complement this. If it's visible over here. So we're just in 2 dimensions, so let's think of it embedded in 3 dimensions. And we have particles here. And ideal anyons would be just point particles. And they would, in space-time, they would somehow move around. And maybe they can braid, sort of, in space-time. And I would typically consider it in the plane, and then there's some, this is maybe not, it's a different thing, but this is a trapping potential. It's typically, let's think about the harmonic trap, so x squared, or if you want some physical constants in there. So this is what I have here. This is just the harmonic potential. So it's essentially just the usual harmonic oscillator problem, but now we have a requirement on the wave functions that if you exchange 2 particles, you get not just plus or minus 1, you can get some arbitrary phase. And that's possible in 2 dimensions, but it's more complicated because you have to care about how that's done. So you have to trace the exchange and do continuous exchanges and so on. And we have a way of modeling that using magnetics. But for now, or if you want, you can think of multi-valued functions or having some kind of topological boundary conditions, which makes it very complicated. So if you want, you can study this problem, and you say, in the bosonic side, so, in this picture, if this works, no? There's always a problem with these things. So here's the bosonic case, where you just have n bosons in a harmonic oscillator, and here's n is the number of particles, so it's just n times, the ground state energy in the harmonic oscillator, so it's just a Gaussian. And on the other side, you have the fermionic, so when this is -1. And then you have, you have Pauli's exclusion principle. You can't put them in the same state. You have to put in different states. So you just sum up the eigenvalues of the harmonic oscillator up to the number of particles you have. And then that goes like n to the 3/2, not like n. So this problem has been studied since a long time. So these pictures come from work of Chitra and Sen in '92. Where they sort of summarize, I like these pictures, it sort of summarizes this picture. It turns out that the picture is quite complicated if you want to interpolate between bosons and fermions. So sometimes it's said that the anyons interpolate between bosons and fermions, but then you have to say, what do you mean with that? So it's clear on the phase side that you can make an interpolation, in the exchange side of quantum statistics. You can say, you can start from 0 and go towards 1 if you normalize by pi. So 0 is boson, 1 is fermion. But making a nice continuous interpolation in the exchange phase doesn't tell you what happens on the exclusion side. So the problem is, what about the relationship between exchange and exclusion? That's the main problem here. So we see in this picture that it's not so simple, and things can happen on the way, and indeed that's sort of what we see. But in this paper, they nevertheless conjecture something, at least that there will be these kind of some states. So okay, there was an understanding, even analytically, that there's some linear interpolation from, if you take some bosonic looking state, then which varies in alpha, this statistics parameter, then it goes linearly up in energy and goes, it overshoots quite much the fermionic energy. So it goes like n squared over there. And so there will be something else on the fermionic side, but also in the middle. Maybe I should use this one. I don't know, does it work? So in the middle here, you have these some kind of states which should have a lower energy. And it has to sort of vary in a complicated way. With essentially the angular momentum has to change as you go up. And these states are unknown analytically, but in some numerics you can see sort of traces of them. Basically the numeric is also very limited. It's been for 3-4 particles, maybe a little bit more on a lattice. So yeah, not so much information. Still, this was the conjecture, and you can say, okay, what if I follow the lowest point here and make some kind of envelope of this? Then maybe I can say something more. And then indeed, they conjecture that there will be some dependence, like square root of the statistics parameter with some factor. And then, but a factor that they estimated would overshoot essentially the fermionic energy if you go to 1 here. And the fermionic energy, okay, this is what you get when you do this. It's a basic exercise to sum up the eigenvalues of the harmonic oscillator. You get this number. That's the Fermi energy in that problem. So yeah, so this was sort of the rough picture. And we started looking at this with John Philip and could only make some very rough estimates of the energy. We could also see something possibly interesting depending on the statistics parameter, that maybe it's stronger or weaker for certain fractions. And we improved these estimates with Larsson and Schrödinger. And then we studied essentially this problem, what about, can you say something better when you go close to bosons or close to fermions? So with Michele and Nicolas, we studied the close to bosons, so almost bosonic. So that's what I'm going to focus on here today. And but also Nicolas and Teotim, they studied the almost fermionic limit. So what we can say is we can somehow revise these estimates a little bit, or the almost fermionic looks kind of legit, that there's some stability there. It sort of, you can perturb a little bit, but it looks like the Fermi energy should be the one. But again, yeah, I will come to why it's more complicated. But now, at least we can say that this was a maybe too rough estimate. It used the assumption that the functions are radially symmetric and so on. It looks like maybe this is a little bit bigger, this factor, but that it is actually kind of much bigger than the factor 1. So that it will be something more complicated in between here. Okay, so that's the start. Yes?
Silly question. What happened to these local minima from the left picture and the right?
Yeah, so this is just a very rough picture that maybe they vanish, but maybe they don't vanish. It could be that there's some fractal landscape there. I'm leaning towards some kind of. So there will be local minima in there.
Asymptotics and
yeah.
in the middle there could be.
Yeah. So this is some approximate curve. Okay. But you see, yeah, here we really don't have even the constant. If you compare to Li Huang-Yang business, this is the first constant is unknown here. So we can do some numerics to find out more. So another complication here is that in the physics literature they also see that, okay, this was essentially for ideal anyons, but you could also have some other types of anyons. And so for instance, there's this work in the 90s also, early 90s, where they look, this is the actual three-body spectrum, interpolating from 0 to 1. And these curves are the ideal ones. So the linear one is analytically known. The nonlinear is not analytically known, but numerically estimated. But then there is also this kind of curve. But that is interpreted to be associated to a different type of anyon. So these are these are point interacting anyons or singular anyons. So these are the singular anyons. They would have a lower energy going down, and actually at some point they would drop out of the Hilbert space. So we could somehow make a, okay, you can also write down functions which behave like that. So these are the type that Benjamin talked about this morning. Jastrow times, or it's Hartree Jastrow, or this is the Gaussian, then it's just sort of a Hartree factor here. So depending on which one you want to look at, so the ideal problem would be with the plus sign here. So this is what we call ideal anyons. They are regular, so they vanish at the diagonal, so they have some exclusion there. But there are these other ones, which we're seeing in the spectrum, and they are singular anyons, or for concreteness, we like to call them chynions, because they are, so in the two-body problem, you can study this and understand it completely, and then it corresponds to the Friedrich extension or the Klein extension. So and this has been studied by a number of people. Michele has and co-workers has been looking at these point interactions. So now let's go to what we can do and in the almost bosonic problem. And we can separate the length scale. So we want to essentially look at these ideal anyons or point-like anyons, but let's do it by first extending the flux, or extending the size of the particles and then taking that to 0. But let's look at 3 different length scales. So you have the size of that, the flux, this magnetic flux that is interacting, which is attached to the particles. And then you have essentially the interparticle scale, so it's also in line with Benjamin's talk, like some intermediate length scale, which could be related to the density. And then you have that's sort of a mesoscopic scale, and then you have a macroscopic scale, which is the scale of the trap, or where your problem is situated. So you could put that to 1, or in the harmonic oscillator, maybe it's related to the frequency there. So, and then you have 3 different models to look at. And the idea is to try to derive one from the other. So the microscopic model is sort of what we start from, how we concretely define these anyons. So we would say, okay, it's bosons, but with some flux attachment. So this is n-body Hamiltonian, and we add some magnetic term here, and put the coupling constant to be alpha. And that magnetic term is, okay, so magnetic potential, and the corresponding magnetic field is this one. So it's basically, a flux disk here related to each particle, each other particle. So this is what particle J sees. So flux disk of size R. And then it's normalized so that, you have a unit of flux on each one. And then alpha is then the unit of, or sort of, the units of flux attached to each particle. But in this model, we also allow for an additional, like a spin-orbit coupling term here, to explore the possibility to have different types of anyons. So maybe some are more repulsive, some are more attractive. So the idea is to put in this, coupling constant G here, to this actual magnetic field. Okay, and then...
Should I now think of the particles as being bosons here? Or?
Yeah, they are bosons, exactly. So I think in the next slide, there they are. So, and then the mesoscopic model on the intermediate scale, this, I don't know, we have been struggling with the name of this because it's not available in the literature, but somehow it has to do with Chern-Simons-Schrödinger, but also Ginsburg-Landau Higgs. Pauli is also, yeah, exactly. Because it's a 2D, like Pauli model, because depending on how you choose this, it's like the coupling to the magnetic field. So, it's an average field model was the original one, but with this extra term, it's more like a Pauli version of this. Okay, so, but for simplicity, I will just call it Chern-Simons-Schrödinger.
But why not Lundholm?
No, no, you should not do that. So, then we have now a flux, a total flux that each particle sees. That's n-1 times alpha. And the idea is to sort of take alpha small now in the almost bosonic sense to make this beta some kind of concrete number. And gamma is an additional parameter that then describes sort of the scalar self-interaction in this problem, or if you want, like a spin-orbit self-interaction. So we have a magnetic self-interaction, and this magnetic field is now bound to the density itself. So it's a one-body model, and so the magnetic field is essentially the field generated by that particle, the particle's density distribution. And it sees itself through its magnetic field. Also, it sees itself through this extra interaction parameter, gamma. So, and then you have the potential. So make this external potential. You can think of the harmonic oscillator. So, and then you can say, okay, but what is gamma? We don't know what gamma is. So that's one of the results, is to derive a gamma, depending on these microscopic parameters. Okay, and then, once you have this model, you can then try to go over to the macroscopic side and see, okay, can I say something more simple, like a density function of Thomas Fermi type? And indeed, you can. And so this density here is not the actual density given by this, but some kind of average density. Because what happens is, as beta becomes larger, that's the total number of flux units, then vortices are created in the system. And we can study this numerically. And then as vortices are created, it's more like a vortex lattice. So the actual density should be some kind of average over this lattice. So you can see this. So this is now a Thomas Fermi functional, I hope you're familiar with. And with the potential, and then there's a big G here, and that will be somehow some coupling constant which depends on all the previous things. So what we see numerically is that it looks like 2 pi beta times some constant, which then depends on the ratio between gamma and beta, if beta is taken, if you sort of fix the ratio and take beta large. So we will come back to this. Okay, so the first result is about this. So the first one is to find out the gamma. Okay, so what we can do is to somehow look at the two-body problem. If you say, okay, when alpha is small, we somehow expect to be in a dilute regime, where the particles basically only see their nearest neighbor. And then you can incorporate the other interactions sort of through this magnetic interaction. So we're now seeing, okay, how can I modify, like, as a Jastrow ansatz, as Benjamin talked about earlier, like, how can I modify the wave function to accommodate the correlations on small scales? So we can look at some kind of toy problem here, just a relative two-body anyon problem, and this is then coming from, this part is from the magnetic potential. And it's, if R, okay, I should have maybe defined what this means. This is the maximum, this is the maximum of R and X, or the modulus of X. So it sort of cuts this, which is singular if R is 0. So then if R is 0, this is just 1 over X squared. But this is a cutoff, which regularizes this stuff. And then you have this magnetic, the spin orbit coupling. So if you look at this problem, you can sort of say, okay, R is going to be small, and let's fix L to be 1 here, and study this two-body problem, or this relative two-body problem, and you minimize your functions, f, with respect to this problem. Then it turns out that you can describe it, okay, to a pretty good approximation by something concrete. So essentially it's just a constant up to size r. Then it goes like some constant times r to alpha plus some other constant times r to the minus alpha. So, and you just have to match up the constants, and then there's a kind of, as you get to L, like in Benjamin's talk, you cut things up to 1. So, so this is sort of some simple interpolating function, and it has the right energy as alpha goes to 0. So it's actually the minimizer approximately, and then you get some funny combination of these constants. So, so if you take this combination of constants and you say, okay, this is the energy, the two-body energy, let's multiply this by the number of pairs, and there's also a factor 2 for the relative mass, then you get the gamma that we have here. So there's a certain gamma that you can get, which then depends on the different parameters. Okay, you don't have to remember everything here, but okay. So the derivation is you can use this kind of ansatz, a Hartree-Jastrow ansatz. So this is the Hartree part, some condensation in a state U, and then there's the Jastrow part, and then you have to rescale it a little bit with this L, depending on which scale you want to look at. And we take the size of the anyons very small, so exponentially small in n, and sigma here is then a constant to regulate how small. And then this L, the mesoscopic scale, should be much bigger but still small. So that, depending on, of course, it will be sort of a dense problem because you're pushing in a lot of particles into some potential. So, but with these assumptions that it's essentially exponential but smaller than this mesoscopic scale, the mesoscopic scale should be sort of small enough, and that your spin orbit is non-negative, then you can prove that this the energy of that state together with the normalization, because you could also put the normalization constant. So energy per particle converges into this Chern-Simons-Schrödinger energy with this specific constant. So it's 2 pi beta, and then there's some combination of g's, and then there's something depending on beta and this essentially this diluteness parameter sigma here. So let's make some interesting observations, and that's for different cases of gamma. So there's a special case when g is equal to 2 here. You can call some kind of supersymmetric case. And then this gamma just doesn't depend on the scale, on this sigma. So it's the same all the time, and it's just 2 pi beta. So there's some kind of scale invariance there. But in the case, let's see, a case that we have considered before was when there was no spin-orbit interaction. So g is equal to 0. Then you can see that it's modified. So what we had then was that gamma was 0, which is true. But oh, sorry, I should have changed. These omegas should be sigma here. Sorry, I changed the notation. So so this should be depending on sigma, and it's 0 when sigma is 0, but then it goes into 2 pi beta. So sort of 2 pi beta seems to be the right constant for ideal anyons when they're really point-like. Except possibly if you go with a negative g, which is also interesting and something to be done. But here we always study this non-negative g. Okay. Yeah. So also this case gamma is equal to 2 plus minus 2 pi beta had been sort of an interest in the literature because it has to do with some kind of self-duality in this problem. So I don't know if you're familiar with the literature, but there's a lot of literature on these kind of self-dual Chern-Simons things. So, okay, so maybe this is what I wanted to say in this case. We had, yeah, maybe another case is if you don't take, essentially if you don't take this small, I don't know, you can also do the original case, like without the Jastrow. You just put the f to be 1, and then study, for instance, well, okay, you can have d equals to 0. That has been looked at before. Then you can derive both the upper bounds and the lower bounds. But in that case, you don't have to worry about yeah, this tau and things like this.
Can you go back to the original formulation with the,
Which one?
this one? Yeah.
This one.
Yeah, so I'm just a bit confused. This A that you had there, the AJ of R,
Yeah.
that really depends on where all the other parts
Exactly. That's defined in the
are.
earlier.
It's the same with the B.
No. Yeah, so I haven't written down what AA is, but AA is the potential associated to this,
Right.
but it's divergence less, and it goes to 0 at infinity.
So if you wanted to think of the Pauli operator, you should really think of the minus G.
Yeah, you can have both. You can have a +1 and a -1. So indeed, so that corresponds to G plus or minus 2.
Right.
So indeed, in the Pauli case, if you have the correct couple, or whatever this special coupling, which is the supersymmetric case, then you can complete the square of the Pauli operator. so that indeed you see this kind of supersymmetry here as well.
So for G down to -2, it's still a positive operator.
Yes. So we can now see, let me say something more about this. So stability. So this non-negativity has to do with stability. And so you can say, okay, for how negative can my gamma be before the model becomes unstable? And indeed, if beta is large enough, it is really this minus 2 pi beta. That if you want the Pauli, the negative Pauli thing. But if beta is 2 or smaller than 2, there's a different, you can have a little bit more attraction before you get instability. So if you think about this, let's go back to the definition of the model. So this is the functional. So I'm playing now with both beta and gamma here. So beta is on the horizontal axis, gamma is on the vertical axis. So you see, if beta is 0, this is the ordinary Gauss-Pitevsky functional. That's with no external magnetic field. So then gamma is really the interaction in the Gauss-Pitevsky. And indeed, we heard also in Charlotte's talk that there is a critical value for gamma where you have a collapse. So due to the uncertainty principle, there is some stability here. And you can lower this, you can make it more attractive up to the critical one. So we call this is the Gagliardo-Nirenberg or Ladysenskaya Gagliardo-Nirenberg constant. So you can go until then, and then you have until you get instability. But as beta increases, you gain some stability. So and we don't know exactly how it looks in here, but we know it's a bit, it's bigger than, or lower if you want, than both of these two blue dashed lines here. And then at some point we know exactly what it is, and that's from 2 and onwards. And it essentially goes linearly between certain special points, and those we call nonlinear Landau levels, because it's very similar to the usual Landau level problem. And you look at the lowest Landau level. So to illustrate this, I have this line down here. So if you look at the usual one-body problem in 2 dimensions, and you have an external magnetic field, let's take a constant external magnetic field if you want, and the associated magnetic potential. And then, so if you subtract that constant, then if you look at the kernel of this, that's exactly the lowest Landau level in the usual Landau problem. And then you can sort of find out what it is. Well, there's a way of factorizing this. That's the supersymmetry. Somehow you can factorize this thing. And then you see that it's essentially like a dz or dz bar acting on something. And this turns out to be, well, psi has to be a solution to a certain equation. So in that constant problem, it's just the Laplace equation. And if you solve it, you get the Gaussian, and then you have u. So after multiplying by some Gaussian factor, you should get something which is annihilated by a d bar or something. So that's just the fact that you have analytic functions times some Gaussian. So here it's very similar. You can do it. It's of course much more complicated, but But you can essentially do the same kind of factorization. However, this psi here, you can call up super potential if you want. This, which produces the magnetic potential, this one has to solve some kind of nonlinear equation here. And the nonlinear equation is a Liouville equation, or a generalized Liouville equation. So we had to go into that business. So let's see what we are in time here. So yeah, so maybe I can just say a few words about, well, we had, so essentially you have a critical coupling. So this red, so we had a critical coupling, which is like the most negative gamma before you get instability. And also you can simplify the problem by just looking at, you don't have to consider the external potential, you can just look at 0 and so on. And you can define this critical, yeah, the critical coupling. So it's really the sort of, if you look at the infimum of the magnetic kinetic term, so this is, if you go back, that's just this term when I ignore the other stuff. And then I divide, it's just the ratio between this term and that term, essentially. So you can define this, and then you look at its infimum, try to minimize this ratio. That will be the critical coupling. So then you can use diamagnetic inequality and say, okay, you can always bound it, you can bound away the magnetic stuff and just look at the kinetic stuff. And then, you know, then we are back to this Gagliardo-Nirenberg problem. So that's the optimal constant in this problem. You know, this, you can look at the solution of nonlinear Schrödinger. And you know, that you get some explicit constant numerically. But also you had this bound, which we talked about, Pauli bound, or Bogomolny bound. Many names. So yeah, so essentially by this, this is non-negative, so you have a bound of this magnetic kinetic in terms of the magnetic field term. So yeah, that's, so the first one here gives you the bound with respect to this line, and the other one gives you the bound with respect to this linear line here. Okay, so a theorem concerning this is about this nonlinear Landau level. So if you want, there's a magnetic stability in 2D. So, so we can say something about this critical coupling. That's what I said in the picture. It's bigger than this Ladyzenskaya, Gagliardo-Nirenberg, and the linear one. And, but then it becomes exactly that, if beta is bigger than or equal to 2. Also, you can study the minimizers, and it turns out they only exist, let's see. So if you look at the critical line here, there will only be minimizers to this problem at these green points. So those are the nonlinear Landau levels. So, and that has to do with how things have to sort of match up, and that you have analytic functions, you know, with the, yeah, and single valuedness and things like this, which is in this problem. So it turns out you can have an explicit form for these minimizers. So they will be of the form of like okay, you take two complex polynomials, P and Q. They have to have a certain degree, which is related to beta. And because of this condition, beta has to be quantized. And then it's the Wronskian of these polynomials divided by an amplitude. And in some package like this. And actually these have been studied a long time ago again, but maybe not in this form. But Jackiw and Pi, they found these kind of functions. The problem was also studied by Hagen and Horvath and Yera. But we never found like a solid, complete proof of this, so we had to do it ourselves. And essentially the technique is through this kind of supersymmetric factorization, going back to Arnold, Kasher, and so on. And we use also this theorem for the generalized Liouville equation. So I told you about this psi here, the superpotential. So we have a requirement. So you want the superpotential such that it gives you the magnetic potential. But the magnetic potential, if you take the curl of it, you should get the density back. That was that the magnetic field generates its own density somehow. So that gives you this nonlinear equation, and the nonlinear equation is exactly this Liouville equation. So on the side of psi, it will look like this, and where f is some polynomial, and it's related to the function u through this factorization. So this would be the Gaussian in the linear problem, and here is the analytic function in both problems. But if you write it in terms of the density instead, then you get this, which is maybe more familiar, Liouville equation, and generalized because the usual Liouville equation doesn't have these delta terms. So it turns out you can, so you have a complete family of solutions of this in terms of these polynomials. So I should move on maybe and show you something more. So so here, just to show you maybe what the problem looks like from a perspective of PDEs, like the corresponding nonlinear, nonlocal PDE related to this problem is this one. So where A is then given by U. Maybe I didn't tell you explicitly what it was, but let's see. So A is this, again, I want to have a magnetic field which is then 2 pi beta times the density. So a way of getting that is to convolve the density with the grad perp of the log. Because if I take the curl, which is the grad perp scalar product of this, I get grad perp, which is the Laplacian. Well, grad perp, nabla perp, yeah, we get the Laplacian. Acting on the log, you get 2 pi delta. So, and convolve with rho, you get what you want. So this is the magnetic potential. And let's see. So so this would be the corresponding equation, but we have also this would be the usual nonlinearity in the, if beta is 0, all of this depends on beta here. But because of this self-generated problem, you have these additional complicated terms. So it's a bit tough to study, but you can do something with the radially symmetric case, or that is easier, of course. So an obvious radially symmetric case is this when beta is 0, so that was the usual Gross-Pitevsky problem in 2D. Then you have this, you know what the critical one is. That's this, it's actually has a name in the physics literature, the Townes soliton, in this paper, from the 60s. That satisfies this critical equation. But so next case, which is simple, is what you can call versiera. Well, that's the name of this function if you look at the radial, in a radial coordinate. So that corresponds then to this point here. So we know exactly how the nonlinear Landau level looks there. It's just this versiera and its rescalings. You can translate it around, you can rescale it, and multiply by phase. So that was the versiera. But also you can do for any of the Landau levels, nonlinear Landau levels, you can do vortex ring. Or we call it vortex ring. I don't know, maybe you have a different name. But there's this explicit function. So this just corresponds to taking, maybe I could have written this here. Here you just take p equals z and q equals 1, those polynomials. That gives you versiera. And here you just take p equals z to the n and q equals 1. You get the vortex ring. So simple choices of p's and q's give you these things. Okay, and the benefit of having those functions is that they're radial, so you can actually, their density is radial, so you can plug them in and try to optimize the energy. So we have done that, but we have also studied it numerically. So here is a little bit of the numerics. So, well, I should have coded. So for the original case, when gamma is equal to 0, which corresponds to the G equals 0, then no spin, when you don't have spin orbit coupling. So in some sense, it's not ideal anyons, it's a little bit softer anyons. And that case had been also studied in work with Michele and Nicolas and Romain de Bosque numerically. So what we did is to extend that analysis, include this gamma, and play with the gamma. And it was super helpful to play with the gamma to understand what kind of theorems we can prove, on the math side. So here's a case when you have 10 units of flux, and gamma is then 2 pi beta, so 20 pi, and a harmonic trap. And then you can, it looks, this is among the smallest energies we can get. Of course, you can play around a bit and say, either you have how many vortices should you have? So essentially in our numerics, we start with some initial state and we evolve it using some gradient descent algorithm in MATLAB. And then it depends on where you start. So, okay, if you start very far away, so if you start here like with no vortices, then it will kind of quickly descend down to something with a couple of vortices in it. But it depends on, you have to play around a little bit with how many vortices you want to have. So we have studied this with different initial states and get different energies. And then you have to pick, because there's some stability around, there's a local minimum with a certain number of vortices. So then you have to check out a couple of different local minima and see which one is the global minimum. Okay, so this is a density profile. In the center here is the center of the trap. So in the picture I had here, there's things would be put in the bottom of the potential here. And then there are these vortices, so I guess it's 6 vortices in this case. And here's a plot for the phase. So, okay, it looks like discontinuous, but that's just because minus pi and plus pi is the same. So from this picture, you can count also, that you can look at the phase circulation and so on and see that things add up. So you can see that they are singly quantized vortices, and this is sort of what we had seen already. But now we can play with, so here, these pictures correspond to 100. You have beta equals 100. So there are many more vortices. And we can now understand that, okay, there's a linear increase essentially in the vortices as beta increases. And here in the left, you have a very negative gamma, not minus 2 pi beta, because that would be not suitable for the numerics. The numerics breaks down when you hit the critical coupling. And what happens is essentially that these vortices become too small for the resolution of the numerics. And also, so the whole density shrinks. So it's an attraction. So they sort of shrink into the bottom of the potential. But as you take a positive gamma, so here is the sort of ideal anyon case. So you take 2 pi beta. So 200 pi, then the density sort of goes the other way. So the density expands, and you see there's more space between the vortices. So it's kind of natural how this behaves. And then we have computed a lot of energies and done some plots. So I will show you some plots. So we had... here's the gamma equals 2 pi beta case. Yeah. So we start sort of what was an ideal anyon gas then in this almost bosonic limit. And I plotted beta from, well, even -1 up to 11, essentially. And what you can see in this picture is maybe a bit messy, but okay, so it's the harmonic trap, and you have these crosses correspond to states which had no vortex. It's like a real state, if you want. There's no vortex involved. So then it looks like the energy goes linearly up in this again, it's the harmonic oscillator problem. So it's kind of special problem. And then you have a few red dots. So here on the side, you can see how many vortices there are in the states we consider. So, and these are the numerically studied states. We also consider analytically, or it's like a combination between analytics and numerics, taking something which is which we know is in the nonlinear Landau level, is NLL, and then you can distribute the vortices and try to put the vortices in an optimal configuration to lower the energy. So yeah, so most of the points here are coming from this numerical study where, so here's a single vortex. You see it's not as good. Of course, when beta is 0, this is the usual, well, beta is 0 and gamma is 0, because I have this linear relationship. Then that's the usual harmonic oscillator. No problem whatsoever. So you know what the spectrum is, hopefully. Harmonic oscillator. In our units, or where we put the omega and stuff, then we have it's 2, 4, 6, 8, and so on. So that's where you expect the spectrum for the harmonic oscillator. So you should start here with a Gaussian, so indeed real function. But then as you go out with the beta, in this case it goes linearly. But at some point that will be too high, that energy, it goes too high. And there are other states coming in with the better energy. So at some point this one vortex, I can't really use this. So we have a one vortex state which comes in, and around the, what is it here, 2, 3 something, it becomes preferable. And then that's the best case for a little while. And then there's something with maybe 2 vortices coming in, which has a better energy. And then maybe you get confused because there are these solid lines, and the solid lines are the vortex rings, which I showed you in the earlier. Yeah, so the solid lines correspond to this type of states. So they are also trial states, but they will typically not be so good. Only the first one, which is, a single vortex. Well, maybe not even in this case. So, but it's sort of, it follows the same shape. Yeah, so then you have this dashed line here. That's an approximate Thomas Fermi curve, if you want, for the energy. And we can then say, okay, the G in this case looks like, so that corresponds to the energy you get with the Thomas Fermi with this coupling constant G. So essentially, you should think of having, I don't know if it's seen here, but G is approximately 2 pi beta times 1 plus kappa, where gamma is 2 pi beta kappa, but times some C, and I will tell you what this is. So maybe turn on the light so you can see that. Yeah, so from our numerics, we approximate, at least within a few percent, this type of behavior. So if you take gamma going linearly with beta, and kappa is the slope in the picture that I showed you. I don't know if you can see this at the same time. Kappa is essentially the slope of the line you study. Then this is sort of the linear interpolation where if kappa goes to -1, that's the Chern-Simons-Schrödinger case, this becomes 0. But if kappa is equal to 0, we get the one which we had from the numerics, and our numerics estimated this, which is some kind of Abrikosov constant, which is due to this vortex lattice. The energy cannot be 2 pi beta, but it's slightly bigger. And then, so in this case, I put kappa equal to 1 here. In this case, kappa is equal to 1. And then you have this curve. The lower curve, the dotted one, is when you don't have the Abrikosov constant. So that's essentially the theoretical lower bound that you have. So coming from this kind of Bogomolny bound. So yeah, so you see it's slightly higher than that. But let's look at, maybe to get a better picture, I lowered the kappa now. So this was kappa equals 1. Now we lower kappa, this is kappa equals 0. Yeah. So then gamma is 0. So that was the original study that we did in 2019. So yeah, you have a similar picture. However, these vortex ring energies are coming down a little bit. And maybe you can see something interesting happening, maybe not. But let's continue. So here kappa is, I think, minus a half. And then we have, well, it was not as much detail. Here's kappa is minus 0.9. So we're getting close to critical. So essentially here the numerics is still good. So we have no problems, typically no problems with the numerics. So now we can see both analytics and numerics in play. So again, you have this. So now the G became much smaller. So it's 0.2 pi beta times the C, is Abel-Coulson constant. Yeah, so that would be this dash dotted line, and it kind of follows that. But then you have these, again, these nonlinear Landau levels. The radial ones are coming down. And indeed, you would expect somehow that at the critical one, so I show you the next picture is the critical case, where, so the Chern-Simons-Schrödinger case, where you do hit, you know that these nonlinear Landau levels will have 0 energy, and you can somehow rescale things. So essentially things just drop out into the bottom of the potential. So, so that's what's happening here, that the energy goes then actually linearly, or approximately linearly. Again, the numerics is maybe not, well, we can do a little bit of numerics for radial things, but it's kind of unreliable in this case. But it seems to drop linearly from the Gaussian, the harmonic problem, down to 0 here at the Versera case. And then it goes sort of linearly up again. And then you have this other one, the first excited harmonic state, which has 1 vortex. And you have to choose the one which is oriented in the right direction. That drops down to the first vortex ring, actual ring case. And then also sort of goes up again. And then it's probably more complicated in the end. So yeah, so maybe, and in this case, indeed, this G, according to this estimate that I hear here, kappa is equal to -1, so G should be sort of 0. So you see it does drop to 0 on this line. So yeah, so you can see a lot of interesting things in play in the problem. Maybe I can say one word about this NLL. So I don't know if you can see them here, but there are some points which are like the hollow markers, where you look at these nonlinear Landau level states and you try to place the vortices. So we did that using Mathématiques and sort of optimizing, doing numerical integration and optimizing the energy with the placement of the vortices. So essentially, we're trying to approximate these kind of, they are already approximations of the true ground states, but these are kind of high-dimensional numerical approximations. But now we're trying to take these nonlinear Landau level states, which are analytical, and try to approximate these states using them somehow. So we're trying to capture that information. It looks like it's a good strategy, at least for kind of negative gamma, close to critical gamma. So in this case, what I can point out that, okay, I don't know, there's a lot of things going on, but so you can say this is the best radial nonlinear Landau level state around beta equals 8. But it turns out that if you take this, if you So that corresponds to having all the vortices in the middle of the potential. So of course that pushes the density out, and you would rather want to put some of the density in. So that's why it's like it's a balance problem, and you want to bring some density in, and the way you do that is using these, to distribute the vortices, like in this picture. So you want to have a little bit of density close to the bottom of the potential. So it's better to distribute the vortices. And in this case, we have, maybe it's clearer here, that in some cases we can get a better energy than the radial one by distributing the vortices. So this was a case where that gives you a lower energy, and it seems to sort of improve a bit. Here's also another case where it's better. So we're continuing along this direction. You can then, once you have these analytical states, you can play around with them, try to discover what the geometry is. So we have various projects relating to this. So I end with this slide. It's a summary and outlook. That in 2D we have these intermediate exchange statistics and these anyons. And we try to figure out the relationship between exchange and exclusion. We have been looking here at this precise density functional theory at the bosonic limit. You can also do something at the fermionic side. I don't talk about this here, but there are some recent results there. At the moment, mostly numerics. But in this almost bosonic case, I said something about the stability. We have, when beta is large enough, it's a linearly increasing stability. So somehow it gives you, the stability of matter that it becomes extensive as the number of fluxes increase. And you have these special cases which we understand better, these nonlinear Landau levels. It's some kind of manifold. It's not in the linear case, it's a subspace, but here it's some kind of manifold because of the various constraints. And the dimension increases also linearly with beta. And then we can study this effective Thomas Fermi model. And what you can do, many things. So we can study the negative case. It's much more tricky, but it's interesting due to these nonlinear Landau levels and what's happening there. Also the fermionic case. We can also study external fields. We started studying a little bit external fields, like a magnetic field or other potentials. You can change the flux profile. I worked with a very simple flux profile, these disks, but maybe more realistic is to change that a little bit. But then, an interesting direction is to sort of relax some of the assumptions here. So in this Liouville equation, we have assumed certain things, some regularity and some, so you can prove some regularity, but it would be interesting to relax some of the regularity assumptions and also the single valuedness assumption. So say that what if do we have it? Yeah, so what if this Hartree, like this condensate, is multi-valued? What can you say then? And I believe that you can probably get better energies that way or find something interesting in that direction. So that's another thing. And also you can, now that you have these vortex states, you can see what happens when you move them around, like do a Barry phase kind of study. So we have an ongoing study on that. And so I think this is a good time to conclude. Thanks for your attention.
For the
So just a curiosity about the vortices. So do you always see singly quantized vortices in your pictures? And if yes, which I think is the answer, but
yes.
Would you expect the same behavior in non-harmonic traps?
Yeah, it's a very good question. So here, indeed, we see always these singly quantized ones. I have to think about whether you can have. It might be possible to somehow like compress them somehow in different ways by playing around with the traps. We haven't had time actually to do any. Like, okay, in our original study, we did also quartic traps, or some other shapes, but that doesn't tell you much about that question. So indeed, I think it can be interesting to play around with the trap a bit. But maybe you need maybe you can compress them, but not make them multiply quantized.
Other questions?
Maybe I can add another comment to that. So, because also it depends on the gamma, you see. So I think if gamma is very attractive, it could be better to make to do these kind of vortex rings.
But when you say other traps, you mean the stronger trap, right?
Yes.
But what if you had a flat, a box instead?
Yeah, that's also something we looked at. Because indeed, when you want to prove something concerning this, you would do like a local density approximation. You would sort of say, how does it look, locally? It's just a homogeneous gas. So then you do the box problem essentially.
Yes, but
and then they are distributed just like it's a regular lattice. The numerics says, and also that's what we can prove.
Are there other questions? I just had maybe one question. In your limiting theorem, what was the assumption on the sigma?
In which theorem?
The theorem where you proved that it converges to CSS.
Yes. CSS. Yeah, this is from many-body quantum mechanics to CSS.
So you can actually do sigma equal to infinity as well.
Exactly, yeah. So
these are the
that would be the ideal. That's sigma infinity would be r is equal to 0. So that's the ideal case. So you so that you take the simpler, it simplifies this function. Then you just take the r to the alpha as an ansatz. That it removes
but
this.
R is 0 in that case, right?
No, small r to the
capital
function.
R is 0.
Yeah, so capital R is 0 and small r to the alpha. So that, but it's sort of the maybe you would improve it by taking, or I don't know if you can improve, but you can say it should be some kind of Bessel function. This type of problem, because it boils down to a Bessel equation. But this is an approximation of Bessel.
Could you prove the limiting theorem also in the box case?
Well, if you fix the box, I expect you can do. But doing thermodynamic limit.
That's what I was asking.
Yeah, of course.
Are there other questions? If not, let's thank Douglas again.
Yeah.